Hello, my name is Jae Kim, and I'm a PhD student in the MIT Hui Joint Program, where I'm working with Dr. Saira Vella and Dr. Rob Evans to develop new machine learning methodology for analyzing geophysical data of geothermal systems. The intended purpose of our study is to prospect for geothermal resources capable of producing electrical power, although the same resource can also be used to simply heat buildings and water. But what I would like to stress is that geothermal has huge potential to cap our carbon emissions. It is capable of producing about 8% of global electricity demand, serving about 17% of the population. In several countries, mostly in Africa, Central South America, and the Pacific, could potentially obtain 100% of their electricity from geothermal resources. And the biggest promise from geothermal is that it is available day and night all year long, meaning it could supplement power to other energy sources, such as wind and solar energy, that are only available during certain times of the day. Geothermal entails us to look deep into the earth, and for this we have a tool called geophysics, which helps us illuminate the subsurface. The magnetotelluric or MT method is particularly useful for telling us something about the electrical conductivity of the earth, and this is helpful because hot fluids that are associated with geothermal systems are conductive. And to analyze MT data, we usually use what are called inversion methods. Inversion methods entail the inference or estimation of a physical model of the Earth that could explain the observed data, and this is guided by physical principles. The problem is that the solution is non-unique. The real data is limited, and it is riddled with noise. Sometimes, geologically unrealistic models will fit the data just as well as a true model. So to choose the model that is closest to the true model becomes a very difficult task. To address these issues, as well as improve on the computational time and efficiency, we are using machine learning algorithms that will help us invert the MT data and also tell us which is the best model. We plan to train a learning machine using both simulated synthetic data based on realistic resistivity models and real data collected over geothermal systems, including the Basin and Range region in western US, the East African Rift system in Uganda, and potentially from New Zealand and Canada. So far, we have run a few pilot tests as a proof of concept to see whether machine learning is capable of reconstructing resistivity models. We simulated synthetic data from 1D resistivity profiles from Gaps Valley, and then reconstructed the 1D resistivity profiles using machine learning. And though we are still in the pilot stage, our preliminary results look promising. In the following months, we will be expanding to 2D and 3D problems, and then finally start working with real data. Our hope is that our work will kickstart a new trend that combines both physics and AI to solve the most pressing problems that the world faces. Thank you for listening.